We have seen two-position synthesis. We have seen three-position synthesis. Now the next topic is obviously four positions of a moving plane. How can we synthesize when four positions of a moving plane is given? Now, in order to explain this, let us look at what we have seen till now. For two positions of a moving plane, you were able to select any point A on the moving plane and determine its coordinates either relative to the fixed frame or relative to the moving frame, A1 or A, and then determine the homologous points, A1, A2, draw the perpendicular bisector, select A0 anywhere on that perpendicular bisector. Now that means you have to specify two coordinates of A, x, y, either with respect to the moving or fixed frame. And then you can specify the distance of A0 from P12, or the distance of A0 from the midpoint of A1, A2 to A0, or you can specify the angle alpha, which is equal to the crank pi over 2 minus beta over 2, where beta 1, 2 is the crank rotation from position 1 to position 2, that you can specify. Or, in fact, you can specify the crank length, A1, A0, A0 length. Either one of them will be one more parameter. So you have three parameters that can be selected freely. And using kinematic inversion, you can determine A0 first and then determine A1 on the perpendicular bisector to A0, A0, 2. Now, we have one pole for two positions and an angular rotation phi12 about the pole. Those are the invariants. In case of three positions, you can select A anywhere you like, determine the three homologous points. A0 is a fixed point on the fixed frame. That's because once you specify A, 3 points define a circle with center A0, that's it. So you have two parameters. If you use kinematic inversion, you can select A0, A02, A03. You can determine A1 on the perpendicular bisectors as the center of the circle described. Now, in this case, we have three poles, P12, P13, P23, and the image pole, P231, in the first position. We have a pole triangle defined by these three poles. That is the invariant. Now, in case of four positions, anything that we have set for two positions is valid, since you can take two positions at a time. So we have 6 poles, P12, P13, P14, P23, P24, P34. These are the 6 poles of the for 4 positions, if you take 2 at a time. If you take 3 at a time, now you are going to have 4 pole triangles. If you take 3 at a time, for example, 1, 2, 3, 1, 2, 4, 2, 3, 4, will give you 1, 2, 3, positions 1, 2, 3, 1, 4, 1, 2, 4, 1, 3, 4, and 2, 3, 4. You will end up with 4 pole triangles. Now, anything that we have stated for 3 positions of a moving plane will be valid. If you are going to besides these poles, you are going to have image poles. For example, in the first position, you are going to have P231, P241, and P341. The way to determine P231 was you had the image, you have the pole triangle P12, P12, P13, P23. You took the image of P23 with respect to side 1 to determine P231. Now, in order to determine P241, you take the pole triangle P12, P14, P24, take the image of P24 with respect to side 1 of that pole triangle to determine P241. Because anything that we say for 3 positions will apply. Okay, so please do not take the image of P241 with respect to side P12, P13. That's not the pole triangle for P241. P24 is not on that triangle. Okay, that's important. Now, once we determine a point A in 4 positions of a plane, it has to automatically satisfy whatever we have set for 3 positions for 2 positions. Okay? When we determine A, for example, and A0 for 4 positions, it has to automatically satisfy all these 3 positions. It has to automatically satisfy all these 2 positions. Okay? Now, another thing that is particular, now those are what we have learned for 2 and 3 positions, which are valid, still valid for 4 positions. Now, there's something particular about 4 positions, and that is we have what we are going to call complementary poles. Complementary poles are 2 poles that do not have the common subscript. You have 3 complementary poles, P12, P34, P14, P23, P13, P24. These are the complementary poles, or opposite poles sometimes called. The complementary pole quadrilateral, or opposite pole quadrilateral, quadrilateral means 4-sided figure. It is a 4-sided figure, it's a quadrilateral, with complementary poles as it is diagonals. For example, in the first case, it is P23, P14 is one complementary pole, P23, P14. P12, P34, P12, P34 is the other complementary pole. Now we have a quadrilateral. The sides are labeled with the common subscript. For example, this side is 2, 2, 3, 1, 2. This side is 3, 4, 1, 4, so 4. 2, 3, 3, 4, 3. 1, 2, 1, 4, 1. That's how we label the sides. Now, the sides are also directed. That's very important. Consider the 2 opposite sides. This line is it is common for 3, but it moves from 2 to 4. 2 to 4. If that is the direction you are taking for this side 3, this side 4, this side 1, opposite side, must be in the same direction from 2 to 4. It is this arrow. So in certain cases, the diagonals may be, the quadrilaterals may be twisted, as you see in this case. This is side 2, this is side 4. These are the 2 diagonals. P34, P12, P23, P14 are the diagonals. So again, you have to define that directions as shown. This is important. So we have 3 pairs of complementary poles. From these complementary poles, we can form three different opposite pole quadrilaterals. These are three different opposite pole quadrilaterals. These are P12, P34, P14, P23, P12, P34, P13, P34, P14, P23, P13, P24. In case if you are, we are going to consider, when we are going to consider inversion, we have to use the image poles. In the image poles, image opposite pole quadrilaterals will be in the first position. These, the images of these poles with respect to for side 1, for position 1. So it will be P12, P34, 1, P14, P23, 1. These are the image opposite pole quadrilaterals in position 1. Of course, we have image opposite pole quadrilaterals in position 2, position 3, but those are rarely used. We usually use image opposite pole quadrilateral for position 1, as in the case of three-position synthesis. Now, you can always draw a circle through 3 points. If I have 3 homologous points, I can draw a circle. Let us say I have drawn a circle for A1, A2, A3. Now, A4 cannot be at any arbitrary place. A4, in order A4 to be on this circle, anywhere on this circle, let us place it over here, it doesn't matter. Let us consider this point. The angle A2, A3, A1 subtends a chord of this circle this much, from A2 to A1. The angle A2, A4, A1 subtends the same arc length. The chordal angles, not the central angles, the central angles, these are not central angles, these are chordal angles, that subtend the same chord arc length must be equal. This is from geometry. Now, this angle beta must be equal to this angle beta. Okay. If I show the coordinates of A1, A2, A3, A4 with respect to this frame as Z1, Z2, Z3, Z4, fixed frame, in complex numbers. This vector, A3 to A2, A3, A2, will be Z2 minus Z3. Because Z3 plus this vector is going to be equal to Z2, so it is equal to Z3 minus Z2. This vector is going to be equal to Z1 minus Z3. This vector is Z2 minus Z4, A4 to A2. A4 to A3 is Z1 minus Z4. Now, these four vectors, by subtracting Z3 from Z2, we have a complex number. At that complex number, it can also be expressed in polar form as RKL, a magnitude, and then e to I gamma KL, an angle. Gamma KL being the angle made by ALAK with respect to the positive x-axis. Now, this angle beta is the angle Z1, Z3 makes with respect to the horizontal, minus the angle Z2, Z3 makes with respect to the horizontal. So that means this angle beta is equal to gamma 1,3, the angle made by Z1, Z3 with respect to the horizontal, minus gamma 2,3, the angle made by the vector Z2 minus Z3 with the horizontal. Similarly, it should be equal to Z1 minus Z4, the angle made by Z1 minus Z4, gamma 1,4, the angle made by Z2 minus Z4 minus gamma 24 will give you beta. This is the condition that we are going to use. Gamma 13 minus gamma 23 must be equal to gamma 14 minus gamma 24. Then what I can do is, the angle of a complex number is the argument of a complex number. Argument of Z1, Z3 minus argument of Z2, Z3, Z2 minus Z3, sorry, must be equal to argument of Z1 minus Z4 minus argument of Z2 minus Z4. Argument are the angles. Now, that is also equal to beta. Consider left side, because they are similar, so I can consider left side only. If I take theta 1, 2 minus theta 1, two angles, argument of A2 e to I theta 1, theta 2, minus argument A1 e to I theta 1. These are two arguments of two vectors, complex numbers. This argument, this subtraction of the arguments, I can take this complex number, divide by this complex number, A2 over A1, this should be A2 over A1. I'm sorry. Here, this is wrong. A2 over A1, I'll correct it. A2 over A1, e to the I theta 2 minus theta 1. So, this theta 2 minus theta 1, argument of Z1 minus Z3 minus argument of Z2 minus Z3, can be written as argument of R13, I don't know what that is, the magnitude, divided by R23, e to the I, gamma 13 minus gamma 23. This is wrong, but this is right. Okay? Next, if this is the case, if I take this vector, call it Z, divide by its complex conjugate, A e to I theta, A e to minus I theta, is equal to e to the 2I theta. So what I do is, this argument is Z1 minus Z3 divided by Z2 minus Z3. This vector is, this is the division of these two vectors, Z1 minus Z3 divided by Z2 minus Z3. Divided by its complex conjugate, Z1 bar minus Z3 bar, divided by Z2 bar minus Z3 bar. Take this vector, divide by its complex conjugate, or you can express it like this, Z1 minus Z3 divided by Z1 bar minus Z3 bar, inverted Z2 bar minus Z3 bar divided by Z2 minus Z3. And this has to be equal to e to the 2I beta. You can do exactly the same thing for the right-hand side. If you do the same thing for the right-hand side, you end up with Z1 minus Z4, Z1 bar minus Z4 bar, Z2 bar minus Z4 bar, Z2 minus Z4. Now, this is the condition for 4 homologous points to lie on a circle. This equation must be satisfied for 4 homologous points to lie on a circle. This is known as the circle point curve. It is a circle. It is a cubic equation. If you multiply it, you will have, okay, let me show it like this. These are the coordinates of Z are the coordinates of the homologous points, Zi. Now, remember, for two-position synthesis, we derive the equation for a pole Pjk. Pjk is equal to Aj minus Ak, Ek minus Ej, where we, as a shorthand, Ek is equal to e to I phi k. Aj is the vector showing the origin of the moving plane, and phi j is the angle the moving plane makes with respect to the positive x-axis. Now Zj is equal to Aj plus Z e to I phi j. This is Zj, Aj plus Z e to I phi j, that you have seen before. Zj minus Zk is equal to Aj minus Ak, Z Ej minus Ek. Ej being e to I phi j, Ek being e to I phi k. This I can write, take Ej minus Ek parentheses, Ej minus Ek, open up parentheses, Aj minus Ak, Ej minus Ek plus Z. This term, if you look at that term, is minus Pjk. So I can write Zj minus Zk is equal to Ej minus Ek, Z being the vector for the center point, for the circle point, or the point that I want to be on a circle, with respect to the moving frame. Z minus Pjk. Pjk being the pole, Pjk. If we note e to I minus I theta is equal to 1 over e to I theta, which is equal to E bar, okay? E to minus I theta is E bar. So E bar is equal to 1 over E. Can you see it? E bar is equal to 1 over E. Then we take the complex conjugate of Zj minus Zk. Zj bar minus Zk bar will be Ej bar minus Ek bar, Z bar, Pjk bar. But Ej bar, Ek bar will be 1 over Ej, 1 over Ek. This I can write as minus Ej minus Ek divided by Ej Ek, Jk being 1, 2, 3, 4, Z minus Pjk, Z bar minus Pjk bar. Now, this is the complex conjugate of Zj minus Zk. If I take the ratio of the two, notice Ej minus Ek will cancel. Zj minus Zk divided by Zj bar minus Zk bar is equal to Ej minus Ej Ek multiplication, Ej Ek multiplication, Z minus Pjk, Z bar minus Pjk bar. Okay? Pjk being the poles. Okay. Now, if I identify Jk, 1, 2, 1, 3, 1, 4, and 2, 4, remember? This equation was what we have obtained for 4 points to lie on a circle. Okay? Z1, Z2, Z3, Z4 were the vectors giving the coordinates of the homologous points. Now, if I identify Jk as such and substitute into this equation, we obtain Z minus P13 divided by Z1 bar minus P13 bar, E1, E3, times 1 over E2, E3, Z bar minus P23 bar, remember? Z minus P23, this term, is equal to E1 minus E4, Z minus P14 divided by Z bar minus P14 bar, this term, times 1 over minus E2 E4, Z bar minus P24, Z minus P24, this term. Now, if you look at these will cancel. Okay? So you end up with z minus p13 divided by z bar minus p13 bar times z bar minus p23 bar, z minus p23 must be equal to z minus p14, z bar minus p14 bar times z bar minus p24 bar, z minus p24. And this is also equal to e to the 2I beta. You can rearrange terms to obtain z minus p13 divided by z bar minus p13 bar, z minus p24, z bar minus p24 bar. Notice 1, 3, 2, 4 are complementary poles. Z minus p14 divided by z bar minus p14 bar times z minus p23, z bar minus p23 bar. Notice 1, 4 and 2, 3 are complementary poles. Now z, in this case, it cannot be anywhere. Z, the vector that shows the location of a circle point on the moving frame, cannot be anywhere. It has to satisfy this equation. This equation, if you expand it, you are going to have z squared, z bar squared term will cancel. You can try that. Perform cross multiplications, etc. P14, P34 are complex numbers, coordinates of the moving poles on the moving frame. So those are known. So you end up with the highest term is going to be z bar squared, or z bar squared z. It is going to be, and if you expand it into x and y coordinates, you are going to obtain a cubic algebraic equation. It is a cubic curve that you can draw. And you have to select a point A on this curve if you want 4 homologous points to lie on a circle. This is known as the circle point curve. It's a cubic curve. Now we'll see how you can solve this equation. I'll tell you later, but right now we'll confine ourselves to the geometrical meaning of this equation. Now I can do the reverse. This is the pole. Okay, let me say a few things about this curve. Number one, this curve has to pass through the poles P12, P13, P14, P241, P341, and P231. Can you think why? Okay, let me say that. Since, take P12. P12 will be at position P12 in position 1. It will be at the same point P12 in position 2. In position 3, it will be P123. In position 4, it will be P124. Notice, it will have 3 positions for 4 positions of the moving plane. Can you pass a circle through those 3 points? You can always pass a circle through those 3 points. So these poles will be on the circle point curve. Will be on that curve. I'll say some other points in a minute, but Let us consider this equation. I can do the reverse. Now let us go back. The way we have defined, we have obtained this equation, we have derived this equation. Now I'm going to go back. This was the argument of z minus p13 minus the argument of z minus p23 is equal to argument of z minus p14 minus the argument of z minus p24. This is how we have obtained this equation, okay? If you look at the reverse. Now that means if I have a point K on the circle point, K being on the circle point, the angle that it will subtend on the two opposite pole quadrilaterals will be equal and in the same direction. Notice, remember that we said these are directed lines. 1 to 2, 1 to 2, side 3, side 4, side 1. So we have a simple theorem. The angle subtended by a point on the circle point curve with respect to the opposite sides of the pole quadrilaterals are equal or differ by two right angles, pi. They must be equal, those two angles must be equal or can differ by pi. Because this same equation will apply if it is they are different by pi. Now, if I know the poles, determine the pole quadrilaterals, Q points, we have the Q points. If I determine P12, P13, P24, P34, let me show that. P1, P24, P34, P34, P23, and P13. Okay? This is your opposite pole quadrilateral. Okay? This is the opposite poles are P23, P14 is one opposite pole quadrilateral. Is P23, sorry, oh, P12, P12, P13 is one side, side 1. P13, P2, 3, 4, where's P34 is the other side. P34, P24, 1. This is the pole quadrilateral. The opposite sides are 1, 2, 1, 3. Okay, this is side 1 from 2 to 3. This is side 3, 4, 2, 4, side 4 from this is 2 to 3. This is 2 to 3. If I take the if I draw lines from these, they will intersect at this point. Notice if I extend this side and this side, this point is going to subtend the same angle for both opposite pole quadrilaterals. So the intersection of points of the opposite sides of the pole quadrilaterals, Q331, Q141, all these 6 points will lie on that circle point curve. We have 12 points already determined on that curve. These are, let me repeat, the poles, the Q points, what we call Q points, which are the intersection of the opposite sides of the pole quadrilaterals. You have 12 points on the circle point curve. Now, how are you going to determine any other point on the circle point curve? Here is the procedure. You select an opposite pole quadrilateral. For example, in here, it is P12, P14, P231, P341 is one opposite pole quadrilateral. The opposite poles are P231, P14, P341, P12. We take the two opposite sides. I have taken P23 side 3 and side 1. This is side 3, this is side 1. These are the opposite sides. You can as well take side 2 and side 4. No problem, the same thing. You draw perpendicular bisectors to these sides. Remember, these vectors are directed. That's very important. Draw the perpendicular bisectors. Draw a line that makes an angle alpha. Alpha is any angle you select, okay? With respect to P1 to P14. Draw an angle alpha, making an angle P1 to alpha with respect to P1 to P14. This line. Now, this angle alpha is clockwise when measured as such. Going from 1 to 4, this is the vector. Alpha is clockwise. Now, go to the other opposite side. It is from, so this is side 1, 2 to 4. You have to go from 2 to 4, measure angle alpha in counterclockwise direction, the same as this angle alpha, from P to 3. This is side P12, this is P23, this is side 3. Measure that angle alpha. It is going to intersect the perpendicular bisector over here. This angle is going to be equal to beta. This opposite pole quadrilateral will be subtended by an angle beta. This opposite side will be subtended by an angle beta as well. Okay? Or beta pi minus 2 alpha. Okay. Now, all points on this circle subtend the same angle since the central angle and chordal angles are related by halves of the central angle. The chordal angle is half the central angle. This angle is beta over 2. Similarly, this angle is beta over 2. Now, you can draw a circle passing through center with center, the intersection of this line with the perpendicular bisector, passing through the pole P231, P341, this circle, and you draw another circle with center at the intersection of the perpendicular bisector and this line making an angle alpha with respect to P1 to P14. This is the circle. Now, every point on this circle is going to subtend an angle beta over 2. This angle is going to be beta over 2. The intersection of these two circles, K and K prime, consider this point and that point, they will subtend the same angle, this point K, will subtend angle beta over 2 for side 3, and it will also subtend the same angle beta over 2 with the opposite side, the other opposite side, P12, P14, and in the same direction. Also K prime will have the same characteristics, meaning these 2 points, since they subtend equal angles for the opposite sides of the pole quadrilateral, opposite pole quadrilateral, they have to be on the circle point curve. Remember, let me go back. Circle point curve, the angle subtended by a point on the circle point curve with respect to opposite sides of the pole quadrilaterals are equal or differ by 2 right angles pi. This condition is only satisfied, this condition is satisfied with these 2 points. Now, if you change alpha, you obtain another circle, and you obtain another intersection of two intersection points different than this one. These 2 circles, depending on these 2 circles, will be a function of alpha. The radius will change, and they will always pass through the poles. So you are going to have different circles, intersections, and you are going to pointwise obtain a curve. This is the circle point curve. Once you determine this point, let us say you are going to use K as a circle point, you can determine, this is K1, okay? The location of A1, circle point in first position. Then you can determine A2, A3, A4. Simply consider it as a 3-position synthesis. Determine, this is A1, determine A2, A3. Consider it as 3-position synthesis with positions 1, 2, 4. Determine A4, as we have done for 3-position synthesis. So once you determine a point on the circle point curve, you can determine its center. Forget about the 4th point. Consider this, you have found A1. Determine A0 as if it is a 3-point synthesis. That's it. So you don't have to determine A4 even. You know it's going to pass through that circle, that crank is going to pass through A4. Okay? So you can determine A0 as well. Now, if you want to determine center point curve, if you are going to determine circle point curve, you have to use circle point curve in the first position. You have to use the image pole, all the poles at the first position, the location of the poles in the first position. These are P12, P13, P14, P241, P131, P241, P231, and 2434. What else? 121314, 2334, 24. Okay, 2334, 24. So you have to determine the image poles for the other 3 poles to draw the circle point. if you want to draw the center point, if you invert the motion, now all you have to do is, for the circle point, you have to use the poles P12, P13, P14, P241, P341, P231. For the center point, P12, P13, P14, P24, P34, and P23 directly. Okay? Since you have inverted the motion, what is the image pole becomes the pole. So you use that. The Q points will be the intersection of the opposite poles of the pole quadrilaterals, not the image. You don't use the image in this case, you use the original locations. Use one of the opposite pole quadrilaterals formed for pointwise determination of the circle point, of the center point this time. Okay? It's simply by kinematic inversion. All you have to do is, for the circle point, you have to use the poles in the first position. For the center point, you have to use the poles at their that you have found original poles, not the image poles, in the first position. Okay? That's all. That's very easy. All this theory, whatever I have discussed till now, although in different form, I have shown the derivation of this equation, these equations, using complex numbers, which were first made by Freudenstein, as far as I know. Freudenstein was the one who showed the equation of this equation that I have shown for circle point and center point. This is the derivation I have shown. It was first it was proven using synthetic geometry by a gentleman named Ludwig Ernst Hans Burmester. His book is quite famous, Lehrbuch der Kinematik. I have this book, it's tremendous. It was written in 1888 using synthetic geometry. He was a mathematician geometry. He was in geometry, Dresden University. These curves were found by Burmester. In his honor, these curves are also known as Burmester curves. The theory that he has developed is known as Burmester theory. It's all worldwide known as with these names. It is from the Burmester's work we have derived the geometrical construction. Okay, once you have the geometrical construction, I did this geometrical construction by pencil, ruler, and etc. And it's a tremendous task. Take my word. I mean, if you are to do this by common, by protractor, pencil, ruler, it is, determining these Q points, poles, help you quite a lot to see the general characteristics, and later you'll determine a few more points only, because you cannot really draw that curve completely pointwise as such. We shall see another analytical method using the dyad formulation next time. But this is the geometrical construction that we'll see, we'll make using GeoGebra. The problem that I'm going to solve using GeoGebra will be, here are the 4 points. The location of C1, C2, C3, C4 are as shown. The angles are as shown. It has to pass this. You are carrying a glass cup. It has to pass through an obstacle without spilling its content. After which, after it passes through that rectangular piece, it will spill down. Okay, but before that, it shouldn't spill. In the next video, I will show how we can determine the center point or circle point for this 4 positions defined in this problem, and see what we can do, how we can design a 4-bar mechanism to synthesize this motion. That's all.